Okay, welcome everybody. Sorry, I'm a few minutes late. How many people started on milestone 2? How many people have read the handout for milestone 2? Okay, a few. Okay, so it's some progress. So we're going to do a walkthrough of how to get going on milestone 2. I highly recommend. How many plan to work on milestone 2 over a reading week? It's a good idea, right? I think milestone is actually, I like graphics, so I think it's a lot of fun if you do it not at the last minute. If you leave it, it's more open-ended than milestone 1. If you leave it to the last 3 days, it's going to be stressful. If you do a bunch of it over reading week, then it won't be very stressful. So that's my advice. Take some time to relax, but take some time for milestone 2 too. Okay, so what should you do to get started? So download the handout and read it. And there's a walkthrough in that handout that says, okay, how do I get going? I'm going to cover most of that in this tutorial too. Read the ece297 Quick Start Guide. So ece297 is an easy-to-use graphics library that we've written for you, and you can do the whole of milestone 2 just talking to it. If you want to do some advanced features, we'll talk a little bit about in the tutorial right after reading week about how you can do a few more advanced things by kind of going underneath ece297 to the underlying library that it's built on, but you don't have to. But you definitely need to know how to use this interface. So read the Quick Start Guide, and it has an example program in it. Run that example program, look at how it works. That's probably the best documentation you can have. Okay, once you've done that, you're going to modify main.cpp a little bit. So in milestone 1, you didn't have a main. We didn't care about the main. In this milestone, we do. You can have a little bit of a main function because you're going to demo your actual mapper program, which starts in the main function that main.cpp creates to your TA. And then the vast majority of your work is going to be actually building a single function called drawMap that actually can draw any city, okay, and visualize it and let you interact with it. Okay, so modifying your main function. So in your project, you're going to find that you have a little skeleton file, and basically for main.cpp, and your main.cpp can be very simple for this milestone, okay? So it can basically load a map, all right? Then you're going to call this one function, drawMap. That is what you're going to write for milestone 2, and then you're going to close a map, okay? So that could be your main function. And all m2.h defines is basically this one function, drawMap, which doesn't take any parameters. The way drawMap expects to be called is it expects you've done a load map call, so all your data structures are loaded. Then you can call drawMap, it'll visualize the map for you, you can interact with it, and then when it's done, you should call closeMap to clean up the data. Okay, why do you have to do it that way? Because while you're going to demo your main program, like mapper to the TA, we also made unit tests for you in the ece297 exercise. ece297 exercise will basically open and close a bunch of maps. So it's basically going to do a sequence of calling load map, calling draw map, calling close map. It'll do that for Toronto, then it'll do it for New York, then it'll do it for like Boston and Beijing and a bunch of cities. So that you can use the unit tests to help test your code and run Valgrind on them, you want to follow this convention, okay? The draw map assumes that load map's been called, and it assumes that close map is called after it. Does it make sense? So that's the way you should write drawMap. Other than that, you can do anything you want, right? Now, I told you you're writing one function for this milestone. Obviously, it's going to have a lot of helper functions, right? If you wrote one function and it did all the work, it probably would be 500 lines to maybe 1,000 lines to maybe like 3,000 lines long, depending on how detailed you want to be. Do not write that in one function, right? So it should have lots of helpers. Okay, so I want to get going. So how are we going to do this? So one of the things we've emphasized in this course is agile development. Get something working, see how it works, make it better. So the simplest thing I can think of in this milestone is let's just get the graphics going. Okay, so we want to create an empty window. Doesn't do anything very useful, but at least we can get the graphics going. Okay, so this is my goal. ece297, this graphics interface that we've written for you, will automatically create these buttons. So it creates some buttons for you by default. What are these buttons for? They're basically for controlling the view. right? You can zoom in, you can zoom out, you can move around the pan the graphics left, right, etc. Okay, and this button is special. Proceed means close this graphics window, right? And go back to run the rest of the program, which in your case would just be close map. Okay, so how do we do this? So I'm including this m2.h function, or header, sorry. All that header has in it, if you read it, is the declaration of this draw map function and a few instructions, of what I just said. Call load map before you call it. We also need to include two more header files. So these are the header files that define the functions that you can call, right? The external interface, the API to the ece2 graphics interface. Okay, so there's two of them. Application.hpp. HPP is just another .h name. Some people call header files .h, some call them .hpp, so it's just a .h file. So application.hpp defines a class called the application class for ece2. It basically is what you need to start the graphics and to make what are called widgets. Okay, widgets are things like buttons, right, that you can interact with. The other big header file that you need to include is graphics.hpp. Graphics includes what are called primitives. So drawing lines, drawing polygons, and attributes, setting colors, setting line widths. Okay, so application.hpp is about setting up the window and making buttons and kind of control. And graphics.hpp is about drawing detailed stuff. And you're going to draw a lot of stuff in this milestone because it's about visualizing a map. Okay, so we've included both those things. There's some boilerplate code. So I'm going to show you this boilerplate. You can just take it and use it. And usually to set up how many people have written graphics before? Okay, one person maybe. What graphics did you write? Okay, so use Qt. So actually ece2 is layered on top of GTK. GTK is basically it's like an alternative to Qt. Okay, so if you used Qt, you've used kind of the other major graphics package that people use a lot to make applications in C++. So most of the applications you'll see on the UG machines or Linux, they're written on GTK. Many of the ones that you're going to see on Windows are written in Qt. Both of them can run on either platform, but just GTK tends to get used more for Linux. Qt tends to get used more for Windows. So if you know Qt, every library is different, but you know the concepts. But don't worry if you go, wait a second, I've never written graphics before. We assume people haven't written graphics before, okay? So it's fine. But my point was usually to set up, we have a bit of boilerplate here to get the window going. In most graphics libraries like GTK, actually it's a lot more boilerplate, okay? So ece2 kind of packages all that stuff up and it's a lot simpler, okay? Because this is not very many lines to open up a window if you're used to writing graphics programs. Usually it's like 100 lines of code to get the window open. I don't know, what was it like in Qt? It's a lot, yeah. So okay, so an interface builder that helps you some with it? Okay, but yeah, generally graphics, it takes more to get a window going than just like, hello world where you can just print out to the console. So this boilerplate is pretty limited. Okay, so what is this boilerplate? Well, this is saying in the ece2 namespace, so basically all the functions, all the classes that we wrote for ece2, we put in a namespace called ece2, so they don't conflict with any other names. It's just like the std namespace. Okay, inside that namespace, there's a class called application. That's a very important class. And inside that class, it has basically another class inside of it, or another type inside of it called settings. Okay, so we've made a settings object of the right type. And now it's a struct, right? We're gonna get some public data members, so we can just directly set them. So this main UI resource, we're basically saying, what is the main UI resource? A resource is something that's not code, okay, so it's data, but it's needed by your program to run. So the UI resource is actually a data file that describes the layout of those buttons and where you're going to draw and so on. Okay, so we've already made one for you. And that layout that we've made for you has already been put into your project in libstreetmap resources main.ui. If you decide to put some other stuff, other resources, like maybe there's some PNGs that you want to use, like little images you want to draw on the screen, you would put them into this same directory, okay? And you can just use this exactly. So we've already made a graphics layout for you. If you don't change this line, you'll get our graphics layout. We have to also tell ece2gl a couple of important things about where stuff is in this graphics layout. So what is the name of the whole big window? What's called the main window, and we called it main window. And what is the name of the area where you can just draw arbitrary graphics? And we call that main canvas. Canvas is something where you can just draw arbitrary things, not buttons. You can draw like lines and polygons in a city. So you don't have to change any of this, okay? If you don't change the user interface layout, you just use our user interface layout. These are the right settings. Okay, and now I need to start the window. And the way I do that is I basically make an application object, so an ece2gl application, and I'm just going to call it application, and its constructor takes these settings. Okay, so I just built an object that is the ece2gl application, and now I want to start it. So I want to make the window appear. I want it to interact with the user. You know, when you click zoom in and zoom out, I want it to do something. So I called the run method, and that's going to hand control the ece2gl, and it's not going to come back for a long time, right? The person can just keep clicking on this window for days if he or she wants to. So this is sort of an unusual function call, because it doesn't come back right away. It actually just takes control of the program, and it just runs for a long time. It takes 4 optional parameters, and we're going to see a couple of these later. But basically, these are what are called callback functions. You can basically tell ece2gl when certain things happen, here's a function you should call that I wrote. Right now, we don't want to do any of that. So we're just passing in null pointer, which is telling ece2gl, I don't care what happens, just deal with it, right? Like you're not going to call any of my functions. Everybody with me so far? Okay, sounds good. Okay, so this just says what I said. And I think one thing I might have missed. Let's see. Yeah, to get these ece2gl functions, you type ece297 and init2. After you type that command, this ece2gl library will be put into your project. Okay, so you're going to get these files by typing that. It's in the milestone1 or milestone2 handout. Okay. Okay, so this is what our window is going to look like. And I want you to take, and we didn't do anything to create these buttons. Basically, ece2gl creates those for us. And I'm going to basically show you that, so you don't take my word for it. Okay. Let's see, let's make this bigger. Okay, thanks. So I just brought up an example milestone2, and I'm going to basically I'm going to call as my overall graphic setup routine this draw map minimal function. So let's just go look at what that looks like. All right, so here's draw map minimal, and it basically is this code I just showed you. Okay, so it just creates this ece2gl application, and it calls application.run. So let's run it. So let's build this. Let's run it. And I got exactly what I said I'd get, right? So I got an empty window, but it doesn't do anything very interesting. And if I actually clicked on one of these buttons, so I click on zoom in, this is actually not going to go well. So I clicked on zoom in, and it crashed, okay? And the reason it crashed is with the code I've written, it doesn't know how to redraw what's in that graphics area. Okay, so let's do a little more work now. Okay, so it took us only a few lines. We got a window open. But our window doesn't draw anything, and if we click in the buttons, it crashes. So it's not great so far. All right, so what do I need to do? I need to write a little more code. So in order to be able to draw on a canvas, so there's a drawing area in that window, I need to do a bit more. First, I need to set a coordinate system. So this is a class in the ece2gl namespace called rectangle, and I'm making an object called initial world, and it has a constructor that basically will make a rectangle between these 2 points. So I'm passing it 2 points, 0, 0, so x equals 0, y equals 0, and x equals 1,000, y equals 1,000. So I've just constructed a rectangle with those 2 corners, and I then am calling a member function of my application, my ece2gl application, called add canvas. So add canvas is an important one. It basically is how it's setting up the area where I can just draw arbitrary graphics. So we're going to draw my city. So in the main.ui layout that we've given you, the region where you can, the big area in the window where you can draw stuff is called main canvas. So I'm saying use that name. And then there's 2 things I give it. I give it a coordinate system. Coordinate system is just a rectangle. So it's that initial world that I set up. And I give it one other thing. I give it the name of a function. Okay, so this could be anything, but I'm going to make a function that is my screen redrawing routine called draw main canvas. Okay, and draw main canvas is what's called a callback. So it's a function that I wrote, and I'm telling ece2gl its name so that whenever a screen redraw is needed, ece2gl can call it. Okay, ece2gl does not know how to draw my graphics. It can't possibly know how to draw a city. So I have to tell it the name, call this when you need a redraw. I can't call this function myself because I don't know when a redraw is needed, right? It's the ece2gl graphics package that knows when a redraw is needed. So we kind of have to do this. We have to set things up this way. We tell it, this is the name of the function to call. You will call it whenever a redraw is necessary. How many people have used callbacks before? Do you know that term? Have you used it before? Okay, so don't worry, I didn't think you would know it. But yeah, it's a fundamental programming technique when you're doing what's called event-driven programming. And a user interface is event-driven. It means the user is doing stuff, clicking on things, typing keyboard input, etc. And when that's happening, we have libraries, graphics libraries that can help us with that. But basically, they can't do all the work. They know if the person has clicked on something, they know if the screen needs to be redrawn, but they can't know what to do. That's your problem. So in order to tell them what to do, we have to pass them the names of these callback functions. When this happens, call this function. And now you have a way to customize the program. Does it make sense? Okay. So I told ece2gl that this is the name of my screen redrawing routine. So I have to make sure I write that. That's actually why the program crashed before when I clicked on a button, because a screen redraw was needed when I zoomed in, and I had not actually set up a callback function. So it crashed, right? It just tried to call a function. I don't actually know what it did. Basically, it probably just tried to call a random function and it didn't work. So now I've told ece2gl that I have a function called draw main canvas. I need to make sure I write that. Otherwise, it won't compile. And ece2gl is going to call this function. I have to make sure its signature matches exactly what ece2gl wants. So ece2gl expects it to return void, like nothing, and it expects it to take 1 parameter. And the parameter is another class defined in the ece2gl namespace called renderer. Renderer is basically an object that knows how to draw things. You can draw lines, polygons, rectangles, circles, etc. So it passes you a pointer to a renderer object. And why does it pass that to you? Because, well, this is your screen redraw function. So, we're pretty sure you're going to want a renderer so you can draw stuff. And what I'm going to draw, okay, so this renderer has a whole bunch of member functions. They're all documented in these header files. So if you read graphics.hpp, it documents all of these functions. VS Code, your IDE, if you actually go G, dash, it'll actually show you various functions you might want. So there are various ways to figure this out. But we've documented all of this. One of the functions in ece2gl is draw rectangle. And draw rectangle takes 2 points. So we pass it a lower left point and an upper right point. And I'm just going to pass it x equals 0, y equals 0, x equals 1,000, y equals 1,000. So how big should this rectangle be? So let's look back at my coordinate system. So my coordinate system is from 0, 0 to 1,000, 1,000. And then I said draw a rectangle from 0, 0 to 1,000, 1,000. So what do you expect? Is it going to be small on the screen or big on the screen? Yeah. Yeah, it should fill the whole graphics area, right? Won't fill the whole window, but the whole area, which is the canvas, the area I can draw on, should be filled. Okay, so let me go in, and this is what it's going to look like. So I'm going to demo this in a second, but that is a screenshot of what it looks like. Okay, so to do this, whoops, close the wrong window. Can you guys see this? Should I make this text bigger or what? Can anyone see this? Can you see this? What do you think? Is it big enough or not? Yeah, I feel like it's not quite big enough. I'm gonna try, let's see, I think it's Control plus. Okay, is that better or worse? I'm gonna assume that's better. Okay, so I'm just gonna comment out that draw map minimal, and I'm gonna call my next version. So it's called draw map blank canvas. And I won't do this every time, but basically, I just said go to the definition of this. So I right-clicked, said go to definition, and this is exactly what I just showed you, right? This is the code I showed you, and we registered this callback function. So here we're calling it draw main canvas blank, and it basically looks like what I showed you, although I slightly simplified it. So we're actually saying set the color. So that's another thing. You can set attributes on a renderer, and they affect all drawing calls until you change them. So set color, I've said RGB is 000, which is black, okay? And then I say set the line width to 10, that's 10 pixels wide. So I'm going to do a thick line, and then I actually say draw rectangle. And a rectangle is drawn as lines. So it'll be drawn as a thick black line from 0, 0 to 1,000, 1,000. Let's see. If I want to do other things, so you don't have to memorize all this. You go G dash and VS Code will show you all the various options. You know, here are things that you can do with a renderer. So I could, for example, draw an arc, right? So, and it tells me what its parameters are. So this will be your friend. And you can also go examine the header file. So let's get rid of that. Oops. So I go to the very top here. Another way I might learn about this is going into some of the ece2 code. So application was one of the code pieces that we could go into. Right, so I can just navigate in there and I can look at what are the various functions that are available here. Okay, so I can do this in the application. Let's close that. I can go look at the colors. And let's see. And I'm not going to show you anything else. Graphics.hpp is the other interesting one. But these are ways you can see what the functions are. And maybe I'll show you one last way you can do this. Okay, so let's go to here. And okay, so I just clicked, I went to Quarkus and I clicked on the ece2 and GTK Quick Start Guide. So I told you that you should go read this ece2 Quick Start Guide. I told you there's an example program, you can download it there. And if you want to know more about the layer underneath ece2, that's this GTK Quick Start Guide, but don't read that right away. Guys, can you quiet down, please? go read that after you started using ece2gl. The last thing I wanted to show you here is this link. Okay, so there are all sorts of comments in the header files for ece2gl, and those comments are written in a special format called Doxygen. Doxygen basically can be used to automatically create web pages that is documentation for code. So if I go here, I can click on, let's click on namespaces. This basically shows me those comments in a hypertext format. So I can look at, for example, the renderer. I told you the renderer class had a bunch of functions. Here are all those functions. Okay, so I can quickly look at, well, I can draw a rectangle. That's what I'm using right now. I can draw lines. I can rotate, set text rotations, and I can draw text and so on. So I can see all these functions, and let's take a look at set line width. If I click on it, it'll tell me more about it. Okay, so it tells me the line width is in pixels, and that's about it. Okay, so that's another way you can learn the user interface. You can have this document or the API interface. You can have this documentation beside you as you code. Okay, so let's go back here though. So I just showed you, the code that we wrote. So 3 lines of code to draw that rectangle in the thick line and black. So let's build this. Let's run it. And it looks basically like I said. Okay, so the black rectangle fills. Basically this area, this whole big white area is the main canvas. That's where you're going to draw your city. And over here on the right are buttons that you can interact with. So if I zoom in, it gets bigger, right? And I can left click and I can drag the graphics, or I can click these buttons up here to pan, etc. I can pinch to zoom in and out as well. Okay. So I guess, and I hit zoom fit and it goes back to my original view. Okay, so I got 2 questions. First question is, why doesn't this black rectangle fill the whole graphics area, this whole canvas? It fills a lot of it, but not all of it. So why does I made my coordinate from 0, 0 to 1,000, 1,000, and then I drew a rectangle from 0, 0 to 1,000, 1,000. So why doesn't it fill the whole area? So what do you think? Yeah, the x coordinate actually goes probably to about -500, positive 1,500 right now. The reason is the screen's not square. Okay, so ece2gl doesn't want to distort your graphics. So you ask for a coordinate system from 0, 0 to 1,000, 1,000. That doesn't match the aspect ratio of this window. So it just gives you some more visible area, right? Rather than sort of stretching things, which might be confusing. If I actually take this window and I make it square, or make the white part of it square, then it actually will fill the whole thing, okay? But if it's not square, it gives me some extra real estate. So when I zoom out, okay, how does ece2gl know the buttons, etc.? Those have already been set up in ece2gl, so it knows how to redraw the buttons, etc. But how did it know to redraw this rectangle, and how did it get smaller? So you don't necessarily know this, but what do you think is happening here? So I click zoom out, and the rectangle gets smaller. What happened? How did that happen? Because you saw the code I wrote. The code I wrote is very simple, right? I always draw the same rectangle. I say black color, 10 pixels wide, and I draw the same rectangle, 0, 0 to 1,000, 1,000. I didn't write any code to do zoom or anything. So what's happening here? Yeah. Yeah. So yeah. Yes, that's exactly right. Okay, so there's 2 things happening here. First, remember that in this graphics area, ece2gl has no idea what you're drawing. So the only way it can redraw it is it calls that draw main canvas routine that I told it to call. So I told it to call this routine, and I wrote the routine. So that's why I always get a black rectangle, because that's what I wrote there. And it is calling it over and over again. The reason that it's zooming in and out is, yes, inside ece2gl is what's called a transformation matrix. So you ask for a coordinate system that is convenient to you. The actual low-level graphics libraries that we're using, GTK and a couple other ones, they're all pixel-based, okay? Pixels can be inconvenient. because they're, they're integers, they're a function of your screen size, etc. So if I want to draw a city map, I don't really want to do all sorts of conversions to pixels all over my code. That would be a mess. So what we do instead is you choose a coordinate system, and now you draw on that, and EasyGL behind the scenes applies this transformation matrix to figure out the pixels and draw them. When you click zoom in or zoom out, it's changing the transformation matrix, and then it's calling your redraw routine. Your redraw routine does exactly the same things, but the pixels it maps to are different. Does that make sense? Same thing if I actually left click and drag the window around. It's calling my redraw routine over and over again, but with a different transformation matrix. So what I see on the screen moves around. So this is convenient, right? You already have a bunch of functionality that you didn't know. But that's like a good way to write a graphics library. You don't want to actually force the user to do everything in pixels because it's going to be kind of a pain. And you have a lot of low-level code that would kind of migrate all over your program. Does that make sense to everybody? Okay, so I'm going to hit proceed. Remember, proceed means return from that application.run. Okay, so it actually closes the graphics window, and in my program, I don't do anything after that. I just call close map, and I'm done. So let's go back to the slides. Okay, so. Okay, so we managed to draw a window, we managed to draw a rectangle. Let's do a bit more. We want to draw intersections. So in milestone2, you have to basically draw everything in the libstreetmap API. Well, you have to draw streets and features like parks, and you have to draw points of interest. And it's all laid out in the milestone2 handout and rubric. We're going to just draw intersections, okay? Which you might choose to draw in milestone2, but you don't have to. You have to draw streets. If you want to draw intersections, you can, but if you just want to draw the streets, that's okay. But intersections is a bit easier, so that's what we're going to do. So I'm going to make a structure just to organize the data that I'm going to draw to make the code simpler. So I've made a structure that has the latitude and longitude of an intersection. Call that position, and it has the intersection's name. And then I'm going to make that a global variable. So I make a vector of intersection data, right? So this data for every single intersection. And in my draw map, remember resize basically will create, make this intersections vector have an entry, an empty entry for every single, or basically it'll create an entry with the default constructor for every single intersection. Okay, so that line is basically made, a vector now has about 190,000 or 200,000 entries in it, and now I need to fill them in. Okay, so this isn't very hard. To encourage interaction for a chocolate bar, what kind of code would you write here? So thinking about the functions that we've given you in milestone1, you talk to libstreetmap. What are you going to call and will you have a loop or an if statement or what? How are you going to fill in this data? To encourage you to answer, I'm giving you a chocolate bar if you answer this. So what do you think?
So you would go by each position, so that one position.
Okay.
And you would go to move to all the positions and another four of the X and Y.
Well, but how do you call my low-level APIs? Does Streets database have a function that basically? Oh, okay, so call find closest intersection. So I could do that, but notice this intersection data is basically, it's a vector. And so it's not a 2D vector. It's going to be difficult for me to index it by two different, like an X and a Y position or something, right? So I could do it that way, but I mean, I'm doing it in a simpler way where I just want to get the data for every single intersection, index it by its intersection number. So close, so something like that. So how do I figure out how many intersections we're going to see? Can I call Streets database for that? Right, so there's like get num intersections, so I can call that. In fact, I already did that, right? That's how I resized the vector. So I can loop through all the intersections, right? And for every intersection, you can make calls like ask what is its position. So you might not remember the API, but basically you can ask what's the position of that intersection. They give you the lat long, so I'm just going to store that. And you can ask what's its name. We're going to store that. I mean, these are fast enough that if I wanted to, I could say, well, why am I even storing this? Right? I'll just call it when I need it. That's fine too. But to make my examples kind of nice and simple, I'm going to store this in advance. Okay? Okay, so I've done that. Now I want to draw it. Okay? And I don't draw it, draw map is like a setup routine. Draw map gets my window going, gets any data that I need ready. It doesn't actually do the drawing. Where my drawing code goes is in the callback function, because I need that drawing to happen every single time the person zooms in, zooms out, etc. So I can't put it in draw map. It's got to go in a callback. So remember, the callback always has this signature, takes a renderer pointer. I'm going to keep drawing this big rectangle because I like it. So I'll just draw that. What would I do to draw all the intersections? And let's say I want to draw, there is a function in ece2 called fill rectangle. Okay, so it takes 2 points and it draws a filled in rectangle. So roughly, what is this code going to look like? And it's not, if you're going, it doesn't sound that very hard. Well, it's not very hard. So if you're going, is it really that easy? It's just that easy. Go ahead. Yeah, I'm going to give it 2 points. So I'm going to pick those 2 points. So first, I want to draw all the intersections. So how do I call the function for every intersection? Right. So for loop. Okay, so for loop over all the intersections. And then you're saying for every intersection, call fill rectangle 2 points. So what 2 points? So kind of. So I need 2 points that will draw a box around this intersection. So I have the position of the intersection. I've just stored as lat long. Okay. So let's say so there's no one answer to this, right? But the basic idea is I know where this intersection is. Draw a box there. So the way I'm going to do it is I'm going to say, well, first I'll loop through all the intersections. Size t is just basically a synonym for unsigned int, so don't be scared by that. But I'm looping through all the intersections. I'm getting an x coordinate from the longitude. I'm getting a y coordinate from the latitude. And I shouldn't have magic numbers, so I've decided I'm going to draw my rectangles 10 units wide and 10 units high, but I don't want magic numbers, so I know my TA is going to take marks off. I don't do that. So I say width is 10, and I'll say the height is also 10. And then I call this fill rectangle function. It's a member function of the renderer, so I call it through the renderer G, and I pass it 2 points. So I'm going to pass it x, y, which are the latitude and longitude of this intersection, and basically, well, x plus 10 and y plus 10, okay? So 10 by 10 rectangle, lower left corner is the intersection lat long. That's what I've chosen to do. Make sense, everybody? And I want to draw all the intersections. I just have to go through them and draw them all. Okay, so when you do this, this is what you're going to get. So where is my city? Does this look like Toronto? Like if you open up Google Maps and this was Toronto, does this help you? So hopefully this is below your quality standard. Hopefully you're not saying, yeah, it looks awesome. I'm gonna turn that in, my TA is gonna be super enthusiastic, right? So doesn't look quite right. I mean, we do have this rectangle, okay? The rectangle looks good. I left that in, but where are my intersections? Any ideas? And as you do milestone 2, this is gonna happen over and over again. Well, to most groups. Like I wrote this drawing code, where to go, right? It doesn't look right. So what do you think happened here? Yeah, so you look at this and you go, well, they're not there, they're off screen or something. And now you would actually, you might look at your code, you might see a problem. You don't see a problem, you bring up the debugger, or you put in a bunch of print statements, and you see, where am I trying to draw, right? You don't stare at it for a really long time, you start going, I need to see what's going on here. My intersections actually are on the screen right now. Can you guess where they are? It's not many guesses, right? Okay, so that's my intersections. That is Toronto. Okay, so, and I'm gonna demo that to convince you. Okay, so basically go down here, and I've pre-written that version of the code, so we'll just uncomment it, but it's exactly the code I showed you, so I'm not going to show it. I'll build it and run it. Yeah, okay, so there's my window. Let's see, let's hide this. So I can still zoom in. I can move things around by dragging. I can zoom in. But yeah, that is Toronto right there. Okay, so you're going to get kind of little marks on sort of everything, right, for this. Does anybody have an idea of what happened? Why does Toronto look like that? So, yeah, I'll let you think about it for a second, and then I'll tell you the answer in case you don't get it. Okay, so why did it look like that? Any ideas? Okay, so if I didn't really know, like I said, I shouldn't stare at it for too long. I should put it in print statements or bring them to debugger. But what do you think happened? Well, so it's a coordinate system problem, right? So what coordinate system did I say I wanted? Do you remember, right? Well, so that's what my code has. My code is using lat long for the drawing, you're right. The coordinate system I asked for, remember, ece297 will take whatever coordinate system I tell it. There was that initial world object that I passed into it, and it was 0, 0 to 1,000, 1,000. Okay? Now I'm drawing in lat long. How, for Toronto, how much do you think the latitude and longitude of the intersections vary? They vary a lot? Do they go from 0 to 1,000? No, right? So first, latitudes and longitudes don't go to 1,000. Secondly, they're big. The distance between a line of latitude is about 112 kilometers. So that's one line of latitude is more than Toronto, okay? So we're gonna get fractions of a latitude and fractions of a longitude. So my coordinate system doesn't really match how I'm drawing. It doesn't really make sense. All my latitudes and longitudes are basically at about latitude 44, longitude 44. That's where Toronto is, the small deviations. So they're all drawing on top of each other, right? I got exactly what I asked for. If I don't see it right away, once I print it out, hopefully I get the idea. Hey, these are all like 44.333, right? So what's going on? So how do I fix this? So there's two ways to fix it. One is easy, one is horrific. So let's see if you come up with the easy or the horrific one. What do you think? Yeah. So change the coordinate system? Right. Is that what you're saying? Yeah, so you're, okay, where will you convert it? Like there are two ways to convert it. Okay, so you want to don't use latitude and longitude at all anymore. So you're one demo ahead. Good idea. But let's say I don't even realize that's a problem. It is a problem. But let's say I just want to draw still in latitude and longitude. Yeah. Yeah, so the easy way to fix this is, well, why did I ask for 0, 0 to 1,000, 1,000? I chose like a random coordinate system. I shouldn't do that. What would be a more logical coordinate system? So I could do 0 to 180, but that's still pretty big, right? Like Toronto's a tiny fraction of that. So it's a bit better, but it's still, Toronto's gonna look like a dot. And if you go, so it could be a problem. And if I get anything in the southern hemisphere, and there are some cities in the southern hemisphere, they're actually going to be off the screen because it doesn't go negative. So better than 1,000, 0, 0 to 1,000, 1,000 is not fantastic. I'd really like the graphics to come up with just Toronto filling the screen because that's kind of what I would expect, right? Not that I have to go look for some dot and kind of zoom way in on it. How do I do that? Yeah, so I can go through Toronto, I can find the minimum latitude, the maximum latitude, the minimum longitude, the maximum latitude, longitude, and I could basically say, well, that's my coordinate system, right? That's gonna put the city on screen. So that makes perfect sense. So you guys got the right way to do this. The horrific way to do this would be say, change all my drawing calls to just scale everything to be between 0, 0 and 1,000, 1,000. Okay, that would actually work, but it kind of defeats the whole purpose of inside ece297, we put in these coordinate transformations so you never have to do anything like that. So don't do things like that. If you can't draw it in a natural way, think about, am I using a natural coordinate system? Maybe I can make my life a lot easier. Okay, so we're gonna fix this. And I already said this. Okay, so how are we gonna do this? So students ask, does libstreetmap, the API we give you, include maximum longitude and maximum latitude and so on? And the answer is they don't. But you can compute them, okay? So you can compute how you can compute this from the data we give you. So we're trying to draw intersections. So what we can do is we just go through all the intersections looking for the maximum latitude and minimum latitude and so on. So how this is a very standard programming problem. Trying to find the maximum of a group of numbers. Also find the minimum of a group of numbers. So how would I do this? So this is not hard, but just take a shot at it. And at the break, I'm going to remember who answered questions. I'll give you a chocolate bar. So what should I initialize this to? Yeah. Yeah. Oh, yeah, it's even better. Yeah, the standard library actually has a function that'll do this. So you're right. So I could just call standard max, so it's even shorter. What that will do is a for loop, and it's going to do the for loop that I'm going to show you. So basically, this is a classic programming problem. I can basically just say set the maximum latitude to the first latitude, do the same thing for the min latitude, and then basically go through all of my intersections and just keep taking the max of the this point's latitude and my max lat and so on. Okay, so there's other ways to do this, but this for loop will do it for me. You're also right. There are actually algorithms like find, I forget what the name of it is exactly, but it's probably like find max or something in the standard library, and it actually does basically the same code, but then you don't have to write it. Okay, so not very hard to write. Where should I put this code? So I have a few options, but where should I put this code? What do you think? Yeah, load map is a good place. So I could put it inside my redraw function, just recompute it every time I'm going to redraw stuff, and it will work. But I would like my redraw to be fast. One of the things your TA is going to be looking for is your map responsive? It may not be perfectly responsive because we're not trying to kill you guys, okay? But you're trying to make it, not super laggy. So you're trying to make it reasonably fast. And there's some stuff you can do towards that is easy. And one of it is don't do any computation in the redraw routine that you don't have to. Because your redraw routine, when I was like clicking the mouse and just moving stuff around, it's calling the redraw as fast as it can, right? Like if my redraws are fast enough, it'll call redraw 60 times a second. And that's pretty fast, right? That's like 16 milliseconds of redraw. And that makes things look very smooth. That means I'd like to do anything I can get out of my redraw functions, I should try to get out. And this is super easy to get out, right? Instead of doing it in redraw, just do it in load map, store it. It's never going to change. So why do it in the redraw function? Also, I guess I need it before I can start up my window. So I guess the redraw function won't work in this case either. So that's an even better thing. I need it before I can actually create the window. So I got to do it earlier. But in case I ever need max lat and min lat later in my redraw functions, it's also useful to just store it from load map. Okay, so I update the world coordinates. So I just take this min lon, min lat, etc. that I've computed, and I make that my new coordinate system. And that's basically it. Okay, so if I do that, I make that one change to my coordinate system. This is not what I get. Okay, so it's debatable. Is this better or worse than what I had before? I got a black screen. Why do you think I have a black screen? Yeah. My height and width are 10, right? And my coordinate system is latitude and longitude. So this is huge, right? A line of latitude is like 112 kilometers. So I basically say draw every intersection of something that's over 1,000 kilometers big, wide. So that's huge, right? Compared to the scale of Toronto, basically all my intersections are gigantic, so I get a black screen. So I've still got a coordinate problem. I wasn't thinking clearly enough about that 10. Okay, so I could play around with this and just experiment what would be right. If I know how big a line of latitude is, 112 kilometers, then 1/1000th of that is 112 meters. That kind of seems a little more reasonable. Like most intersections are more than 112 meters apart. So it seems like not a crazy one. I can also just do trial and error, right? So I can play around with this size until it looks reasonable. And 0.001 looks pretty good. So I'm going to demo this. I'm going to draw the intersections the same size all the time. So the height and width at 0.001. Question I get from students sometimes is, should I make them change based on the zoom level? Because I zoom in, should this change? So I'm going to draw them the same size all the time. What do you think that's going to make the graphics look like? how will my intersections look as I zoom in? Will they get bigger? Will they stay the same? Will they get smaller? What do you think? They're gonna get bigger, okay? And that may be fine, right? I think that's fine. So as I zoom in, they're gonna get bigger. I just always draw them the same size. It's also easy. If I decide that when I zoom way in, I would like them to look a bit smaller, to be less cluttered, okay, then there are some more functions in ece2 you can use to tell how zoomed in you are. So I could actually change how I draw them if I want, but you don't have to. Okay, so if I do that, I'm gonna get a picture that looks like this. It's actually now starting to look like Toronto. And let me convince you of that by, let's see, let me hide these controls. All right, so I'm gonna basically do this one. So I basically activated those code changes, and now we draw it, and it does look reasonable. And if I zoom in, you can see the intersections do gradually get bigger because I'm always drawing the same thing. And to me, that's a perfectly reasonable design decision. But if you decide that, I think that's too big, then you could put some code in to say, well, stop, draw a bit smaller, and zoom in that far. Your call. What do you think? Does this look right? So does this look like Toronto? Is it correct? So you think, yeah, it looks like Toronto. Anybody else? Any flaws in this? So there is a flaw in this. It does look a lot like Toronto. So it's almost right, okay? But it's not quite right. And your TAs will actually look for this. Like we tell the TAs certain things to look for, so for sure they're gonna catch us if you do it. But because you're at this tutorial, you're not gonna do this. So what's wrong with this? So it's a little bit subtle, perhaps. How wide is Toronto compared to the height? Basically, this looks a little bit spread out horizontally or equivalently squished vertically. Okay, so it looks like Toronto, but its aspect ratio seems a bit distorted. If you actually compare this to Google Maps, you'll find it's not quite right. And if you actually zoom in on, for example, Spadina Circle, which is supposed to be circular, right on campus, you actually see it's an oval. Okay, so it's not quite right. What did we do wrong here? Why does it look wrong? And it's not totally wrong, right? It doesn't look completely crazy. But what do you think? And while you're thinking about that, I'm gonna bring up the slides again. Let's see. Okay, so any ideas? What would you do wrong? Yeah. Yeah, that's exactly right. Okay, so what we've done is we've drawn latitude and longitude directly, and that distorts our map because the Earth is round. Okay, so lines of latitude are always 112 kilometers apart. Lines of longitude at the equator are also 112 kilometers apart. At the north and south poles, they are 0 kilometers apart. They come to a point. Where Toronto is, we're at about 44 degrees. Basically, a line of longitude is about 70% as far apart as a line of latitude. Okay, so by drawing latitude and longitude as if they're equal distance, like that's what we drew, we have basically stretched things horizontally by about 50%, right? Like we drew them, they should be 70% far apart as we drew them, okay? And if we did this for an even further north thing, like Iceland, the distortion would be even bigger. Okay, as we get closer to the poles, the distortion gets worse and worse. So what should we do to fix this? So we shouldn't draw directly in latitude and longitude, right? Because you can't draw on a curved screen. This doesn't make sense. You gotta basically, you gotta do something different. So what do you think? If you read the milestone 1 handout carefully, you already know something in there that will be helpful to you. So we got to change our coordinate system. What should we change it to? Yeah. Yeah, yeah, so there's a formula for projection.
Yeah.
I think it's called the equirectangular projection. So it's a projection that is basically flattens a portion of the Earth, and within a small region is pretty accurate. But you can't draw the Earth on a flat surface without distorting it somehow, but in a local region, the distortion can be very, very small. So there's a projection in milestone 1 that basically projects from latitude and longitude to meters on the surface of the Earth. So it corrects for the fact that latitude and longitude are, well, a longitude is closer together than a latitude, and how close together depends on how far north you are. It has a cosine of the latitude in it. So it converts, and actually it does another nice thing. So it's giving you a proper non-distorted coordinate system that we call just XY coordinates. And those coordinates also have a physical meaning. They are meters on the surface of the Earth. That's actually helpful because if you're now trying to decide, for example, how big to draw a rectangle, your coordinate system is pretty easy to understand, right? It's meters on the surface of the Earth. So let's do that. So if we change our coordinate system, let's see. Well, let me show you how it's done first, then I'll show you what it looks like. So we should convert latitude and longitude, and let me hide this again, to Cartesian XY, right? So just XY on the surface of the Earth. So the milestone one handout tells you how to do this, gives you the formula. We should not scatter that formula all over our program. You're going to be drawing all sorts of stuff, like street segments, points of interest, features. Don't write this formula 100 times. Your TA will be sad, right? And he or she will reluctantly penalize your grade. But your TA really would rather not do that. So you should make helper functions. So I'm going to make a helper function that takes the longitude and makes the x coordinate, and another one that takes the latitude and makes the y coordinate. And I need those. It also can be useful sometimes to have the inverse, so I'm going to make the inverse ones too. I don't need them as much, but I just take the formulas in milestone 1, I use my amazing powers of algebra, I solve for the other side, and I write the other formula too. This needs lat av. Okay, so where does the lat average come from? I didn't pass it into it. And so in my helper function, where do you think lat average is coming from? What else could it be? There's only one other answer, right? So I didn't pass it to it. Where did I get the average latitude? It's not the same for every city, so I certainly shouldn't hard code it. I should not hard code this to be 44, because then my map works for Toronto, doesn't work for anything else. So this isn't a complicated question. What's the other way that this function could know lat average? So I made it a global variable, and I computed it in load map, okay? So you don't have to do that. But again, for speed, I just went, you know what, I'll just compute this in load map, I put it into my global data structure, everybody can use it. So I didn't pass it in, okay? So that's where it is. I made helper functions. I made 2 different helper functions. Probably the code will be, if I look at my code, you're gonna see that I'm usually converting a long and a lat, one right after the other. So probably this is even a little cleaner if I wrote one helper function that just converts a lat long to an XY. I didn't do that, but in your code, you could write it probably even cleaner than this. Okay, so with that code, what I can do is basically, I just change my draw main canvas to convert my longitude to an X coordinate and my latitude to a Y coordinate on the surface of the Earth. And now I go and draw that. Okay, so I've still got my fill rectangle, and I've changed my width and height. Okay, so I was using like 0.001 for lines of latitude and longitude coordinate system. That doesn't make any sense once I changed to XY being meters. 100 meters seems like a reasonable size to draw an intersection. So, and again, that's one of the advantages of this coordinate system is I can kind of reason about it. It's fairly intuitive. Okay, so I've changed my redraw routine. Do I have to change anything else? This is how I set up the window. And there is something I should change. Okay, so I've changed my drawing routine. What else should I change? What do you think? There are not very many lines on here, so there's only so many choices. Yeah, what do you think? Yeah, this is a common problem that students, mistakes that students and I make. If you change how you draw things, you gotta change your coordinate system. Okay, so this coordinate system is no longer reasonable for the way I'm drawing, but I have these nice helper functions. So I can convert my minimum latitude and longitude, etc., to X and Y. That's the coordinate system I want to draw it. Okay, once I do that, I get a corrected projection. Okay, and when you see them side by side, you can see the difference. Right? So that actually does look more like Toronto than this distorted view. And just to convince you this really works, I'll do a last demo and then we'll take a break. Okay, so let's see. Okay, so there's my map, and it looks like Toronto now. Okay, and it interacts, looks good. Okay, so if there are no questions, we're gonna take a break for a few minutes. Let's take a break till maybe 25 after. Okay, I've got quite a few more things to go through, so that might take too long a break. And I owe a few of you chocolate bars, so I'll come give you one. Okay, so we're back. So we fixed the projection, so that's good. Okay, so I already demoed that. I want you to look at this code. Okay, this is the code we used to fix it. So we basically, in our redraw routine, draw main canvas here, we are computing this X and Y by calling these two helper functions. Okay, we do that for like 200,000 intersections or so on every single redraw. Okay, so this is a speed critical routine. The redraw routine is actually probably the only routine whose speed matters a lot in milestone2. Okay, so it's speed critical, and this loop runs maybe 200,000 times in Toronto. In Tokyo, it's like more like 1 million or a bit more than 1 million. Tokyo's really big. So we want to pay attention to, do we add any unnecessary computation here? And we're calling these helper functions. Let's check what's in them. Okay, so if we look at this helper function, my X from ln looks like this. Longitude times one constant times another constant times the cosine of average latitude times some constant. Okay, this is not too bad. Okay, so it's 1, 2, 3, 4 multiplies and a cosine call. And in fact, if you run in release build, which you should, these two multiplications, the compiler's smart. It's multiplying by two constants. When it actually is compiling a program, it just goes and it multiplies those two constants together once, and we'll say just multiply longitude by one constant, a new constant. So that's one of the things that compiler optimizations do that make your program faster. So really, it's like 3 multiplies and a cosine. Not too bad, but we're doing it 200,000 times. Okay, so for a chocolate bar, I'm going to do a math test. I'm going to see how fast you guys are because the processor's doing math here. So let's see, 2 teams. Okay, how about you 2 teams? So this team here versus that team then. You agree? Okay, you give each a simple math question. We're going to see who can answer it faster. And whichever team answers it faster, you all get a chocolate bar. Okay? Are you ready? Do you agree to this, or do you want to basically say, no, it's too much pressure, I can't handle this, right? The competition. You can handle it? Okay. So I'm going to give you guys the question first. Do you want to be the timekeeper? Do you have a cell phone? Okay, so you're going to do a stopwatch. Ready? Okay, so you guys ready for you can confer on this math problem, whatever, or you can shut it out as fast as one of you gets it. Ready? What is 2 times 2? How long did that take them? Maybe a second? 1.6 seconds. Okay, remember that time? Okay? So, okay, your turn. You guys ready? 1.6 seconds, time to beat. What is the cosine of 2? I think we're past 1.6 seconds. Well, that's actually pretty good. You went to your cell phone, right? So that's actually that's pretty good. So, okay, you guys both get prizes. Okay, why did I ask you that question? Cosine is actually a lot harder to compute than multiplication. So in a processor, most processors, including the ones in the UG labs, they can launch a new multiplication every single clock cycle. So the processors we have in the labs run a clock period of about, well, they run 3 billion cycles per second. So every single cycle they do a multiplication. So very fast, not free, but it's fast. Cosine is much harder. Cosine, you have to use a Taylor series expansion or something similar. So it's actually a whole bunch of multiplies and adds and subtracts. It's a lot more work. So the biggest thing in here is actually this cosine, and it's not catastrophic, but it might add up to a bit, okay? So I will give each team like a chocolate bar because that was an unfair question, but I'll do that at the end. Okay, so can we speed this up? Okay, so what can we do to get, and again, this is not a catastrophe, but is there anything simple we could do to make this faster? We're calling this, actually it's more like 200,000 times for Toronto on every single redraw, and we might do, for maps really fast, 60 redraws in a second. So is there anything we can do to get rid of this? It's not very complicated. I don't want to do anything very complicated. What do you think? Yeah, so I can pre-compute the coast. So actually I can compute this in my load map, and that's like one thing to store and I get rid of the cosine. So that's actually a good idea. And I'm going to go one step farther, but if I need this coast anywhere else, that's an excellent idea. It'll make your map faster and it's super easy. I'm going to go one step farther. I'm actually going to compute all these x, y values in load map. Right now I'm storing the lat long. I actually don't care about the lat long that much. What I really want is the x, y. So why don't I just compute that right in load map? So all I do is I change my intersection data so that instead of storing lat long, it's now going to store x, y, and it's actually going to store it in the ece2 2D point, the exact thing that I'm going to pass into the drawing routine. So I'm trying to make this as fast as possible. So my load map basically now just does that same computation. My draw map gets faster, or my redraw gets faster. So my redraw looks a bit simpler. I just go through and you're going to find that ece2 has a lot of overloaded functions for convenience. So fill rectangle I can call with 2 points, but I can also call it with 1 point and a width and a height. So now I'm going to call it with 1 point and a width and a height. Does that make sense? Okay, we're going to talk about this right after reading week, but you shouldn't actually spend much time trying to make a program faster if you can't measure. So I'm going to show you, I've written a bit of code using a library called Chrono. It's part of the standard library that allows you to time code. We're going to talk after reading week about how you can use that and a few other techniques to find slow spots in your code. But that code exists, so I'm just going to run it right now. Okay, so let me bring this up. So basically, well, maybe I'll show you the code really quickly. Actually, I won't show you the code. I showed you this before. Basically, I have a timer around my code. Whoops. I don't know what that is doing. Let's get rid of that. Okay. So I've got a timer around my redraw function. It's actually not a bad idea for you to put in your milestone2 right away, so you can see how fast your redraws are as you're coding. So every time, if you look down here, you can see the output to the terminal. So I'm going to zoom in, and basically that redraw took not long, 7 milliseconds. Okay, I'm going to zoom in again. Okay, it actually got a little faster, about 5 milliseconds, 6 that time, 6, 5, 7. Okay, so it's bouncing around a little bit, but it's basically between 5 and 7. I'm going to do it again. And as I go in, it's like there it was pretty consistently 7, then 6, then 5. Okay. You actually find that ece2 tends to get a bit faster as you zoom in. The reason is it actually does pre-clipping. Okay, so pre-clipping means it does quick tests to see if something's totally off the screen. So if the rectangle is completely off the screen, it never actually calls the underlying graphics library. Drawing a rectangle takes a fair amount of work, right? You got to figure out where the pixels are, draw them all, etc. If you figure out it's off screen, you can short circuit that. So that's the very first thing ece2 does. What that means is as you zoom in and more stuff is off the screen, the program tends to get somewhat faster. So you see it's gone from 7 milliseconds down to 6, and then went back to 7, but it's so there's some bounce, but generally it's faster as it goes in, okay? Okay, this is without pre-computation. This is my original code, and the times I'm getting, okay, so when I'm zoomed out, I'm getting, maybe 8 milliseconds. Okay, so let's get rid of that, and I'm gonna close this version of the program, and I'm gonna go over to another one. Okay, so this basically does the same thing. All I've done is, let me uncomment that. This is basically the rewritten code, where instead of computing XY from lat long, and I think IntelliSense needs a little while to wake up, so, well, take my word for it. It's basically the faster code that I showed you. Okay, let me get rid of this. All right, so build this, run it. It's important if I'm comparing drawing speed that I keep everything the same. So I'm actually not making the window any bigger, and I'm going to zoom in, zoom in and out the same number of times, okay? Because the redraws do change speed depending on what's off screen and so on. Okay, so as I zoom in, it's faster. This is actually taking more like, let's do that again. Okay, so this is now taking like 2 milliseconds. This is really fast, okay? So it's noticeably faster, okay? And the runs that I was just doing there. It's bouncing around between maybe 3 milliseconds and 1 millisecond, but it was a reasonable amount faster. So all these redraws are pretty fast. If I move this or drag this around, it feels pretty smooth, okay? Because my redraws are fast. And I've measured this a few times. So usually it comes out, when you're zoomed out about 1.5 times faster, when you're zoomed in about 2 times faster. There it was maybe even a little more than that. But right now my redraws are so fast that I don't have that much precision on exactly how fast they are. So this was basically a pretty easy way to get some speed up. I didn't show you the code that I used to time that, but it's in the lecture from Thursday. It's basically showed the code in lecture of here's the chrono code that you can use to time a function. So if you want to add that yourself, just go look at the notes from yesterday's lecture. Okay, so that's all I'm going to show you for drawing. But we don't want to just draw, we want to react to what the user does. So one of the things we want to react to is if the user clicks a mouse. Okay? And if you read the milestone2 handout, one of the required features is if a person clicks in the graphics area, you have to figure out what intersection they clicked on, and then you have to highlight it and give some information about it or indicate it somehow, right, that they clicked on this. So this is a required thing you have to do. Okay, in order to make this work, I need to register another callback with EasyGL. So remember I told you that when we call this run function that starts our window, it has 4 callbacks you can pass in, and we were setting them all to null, which means don't call me for anything, right, except screen redraws. Now I'm passing in one of the callbacks. And if you look at the comments above in the header file for application.run, it tells you what every callback is. But the second one is basically a function that will be called when the user clicks a mouse in that main canvas, the area where you're drawing the city. Okay, so what happens is if the user clicks a mouse there, the function that you registered will be called. Okay, so the function that I registered, what I said should be called, is called act on mouse click. And act on mouse click has to have the right signature. Okay, so EasyGL is going to call it, expecting it to take certain parameters. You guys, in 243, you studied how parameters are passed. Is that right? You know, you push them onto the stack and so on. Okay, so ece2gl is going to push those things onto the stack, 4 different variables. It has to go to a function that expects those same 4 types of variables. Otherwise, bad things happen, right? Your program will crash, etc. Also, the compiler won't like it. So you can make this name anything you want, just has to map what you put here, but you cannot change this. Must have that signature. Okay, first thing is a pointer to the ece2gl application. That's because often you might want to call some of its members in this callback function. So that's so that you can access it. You might want to get some information on which mouse button was pushed. So you're passed a pointer to an object from the underlying graphics library that allows you to ask questions like, is the left mouse button pushed? Is shift held down? Is the right mouse button pushed? So if you want to, you can figure out exactly which button was pushed. And then the 2 most important things are you're passed an X and Y coordinate, which is where the person clicked. And these X and Y coordinate are in your coordinate system, okay? So it's convenient for you to work on. So we set a coordinate system that was meters on the surface of the Earth. These will come back meters on the surface of the Earth. The exact same coordinate system. Okay, so I've put in an output line here. Now I need to find what intersection is this. Okay, so it's going to get called whenever the user clicks, but ece2gl has no idea about intersections or what you've drawn or anything. You have to figure out what intersection the person clicked on. And we're going to print it out once we figure it out. Okay, print out the name of that intersection. So how do we figure this out? And the hint is that it fits in that block of code. Okay, so it's not a lot of code, it fits in that gray box. So any ideas? How can we figure this out? There's a couple ways you can do it. If you remember your M1 functions, you might have a very short way to do it. If you don't, you might have a slightly longer way to do it. So what do you think? Yeah, so basically you wrote a find closest intersection function, so you could use that. Now that one actually took lat longs, so we have to convert the coordinates first, but that's perfectly reasonable. We actually wrote these, and that's actually what I did here. Okay, so we wrote these other conversion routines, latitude from Y, longitude from X, so we convert back to lat long, and then we send that to something that we already wrote, find closest intersection, and we're done. Okay, so your M1 functions, several of them will be quite helpful in M2. We had you write those partly to get familiar with our APIs, partly as a learning exercise for data structures, but also they give you some scaffolding to build on. If I didn't remember this function, I could write a new one that basically just goes through all my XY intersection points, which I'm now storing, and figures out which one is closest. So I could do that too, that's fine. But sometimes students ask, well, could I just ask ece2gl? Like, couldn't I just ask it, what's the closest intersection? It has no idea what you're drawing. Okay, graphics packages, all modern graphics packages are what are called immediate mode. Immediate mode means they draw something and they immediately forget. Okay, so it has no idea what's on the screen. If you want to interpret a mouse click, you have to write the code to do it. And so this is called hit testing. And the basic technique is, figure out what's closest to what you clicked on. If you want to be a little more advanced, you could also figure out if there are multiple things there, maybe what's on top, but we don't expect you to do that. Just figure out what's closest, it's fine. So is everybody with me so far? So that's how you have to do hit testing. Figure out what thing is closest to that, usually by looping over them all and checking. Once you have that, I should do something. Okay, so I figured out like what was the closest intersection, and I did print it out. Okay, so I printed it out here, but that's maybe not the most user-friendly thing. I should probably graphically show what did you just do. So here's how I'm doing that. Okay, I found the closest intersection. It's got a certain ID. I can just say the ece2gl application, you can ask it for a renderer object. Okay, so I say, give me the renderer, and I was passed the ece2gl application pointer, so I can get in all of its methods. So I ask it for a renderer pointer, and now I can do anything I want. So I can basically set the color to red, and then I'm going to use fill rectangle again to draw just this one intersection. Okay, but I'm drawing it in red. Does it make sense? So it should show up highlighted. So let me show you what that does. Okay, so let's get rid of this one. All right, so I built it. Now I'm going to run it. Okay, so let's make this bigger. We'll zoom in a bit so we can see better. All right, so you can see where my mouse is, I think, right? So I'm just going to click on this and highlight it. So it's good. I'm going to click on this one, it highlighted. Go over here, I'm going to click on this one and highlight. It's looking good, right? So I'm just going to I'm going to move this over a little and then zoom in, but they all disappeared. Okay, so let's bring it back. Click on that one, click on that one. So highlighted. If I zoom in to see better, they're gone. Let's click on that one. Let's move the view over a little. It's gone. Okay, so what's happening? So I highlight it, but it's disappearing on me all the time. Okay, let's try it one more time. Highlight that. Move the screen over a little. It's gone. What's happening? Yeah. Yeah, so every time I drag the screen around, like what's called panning, or I zoom in or out, I'm doing screen redraws. Okay, so I basically, in my act on mouse button, I did a draw of that one polygon, or that one rectangle, but my redraw function knows nothing about this. As soon as a redraw is invoked, it overwrites it, okay, and everything goes back to black. So does this seem like a good implementation? What do you think? Will TA be happy with this or not? What do you think? Happy, not happy? You think they'll be happy? Okay, so it's not good. We tell the TAs to check for this too, so they're definitely going to check for it. We have had a few students argue this is a design choice. It's like a feature, not a bug. We do not accept that answer. Like if you were writing a document in Microsoft Word and you triggered a screen redraw and your document disappeared, no one would consider that an acceptable visualization interface. So this is not like a design choice. It doesn't work. Okay, so let's go back to the slides again. How am I going to fix this? So what do I do to fix this? Any ideas? Yeah. Yeah, so you need to have a state. So this is a fundamental concept. Because your graphics are going to be redrawn all the time, you can't just, if somebody's clicking on something, you're interacting with the user, you can't just say, oh, highlight this, do this. You need to make it survive. And to make it survive, you need to store some state. So your redraw, if you expect your redraw function to do something different, you got to store state. That's the right way to do it. So let's change how we do this. So we have to use what's called stateful graphics. And the general procedure is always the same. So if we want to have some interaction with the user, we register a callback function. So we've already done that. We registered a function when the mouse is clicked. We have to write that callback function. So in this case, we had to find the intersection closest to the click. We tried drawing it, but that's the wrong thing to do. What we should do instead is we record that it is highlighted. So we have to have a variable that stores it. And that variable has to be accessible to our redraw routine. So the easiest way to do it is to put it in our global state, right? We've got some structure with global variables, we put it there. It's either that, there are a few things that are slight variations on that, but basically we've got to store it somewhere the redraw routine can get at it. Easiest is a global variable. Don't have 20 global variables, so put them in a structure. If you've got a bunch of state for your graphics, make it a class or a struct so they're all grouped together. And then you modify your screen redraw function so that it also looks at the state variable and how it behaves now changes. Okay, so we already did this, right? We registered the callback. When we called application.run, we told it we want mouse clicks, call this routine. And there are 4 callbacks. So just to tell you what they are, there's this act on mouse click, but there's another one for initial setup. Initial setup is useful, you're gonna see it in a minute, but initial setup is useful if there's something you wanna do right after the window pops up. Okay, that's what that callback is for. There's one that gets called whenever the mouse moves. So if you wanna maybe pop up tooltips or something, this can be useful. And there's one when the person hits a keyboard in the graphics area. So they hit the keyboard where the main canvas is. Okay, so you can use all 4 of those callbacks if you want, or you don't have to use them all if you don't want to. Okay, so we already did this. We found the closest intersection. And now what we need to do, though, is we shouldn't just draw that highlighted. I'm going to add in my intersection data. Remember, that was a global variable that I set up in load map. Well, I'm going to add a highlight flag to it. So every intersection now has a flag of whether it's highlighted or not. I'm going to default it to false. So when I first create this vector, it'll be nobody's highlighted. But now in this click routine, mouse click handler, once I find the proper intersection ID, I set its highlight variable to true. Okay? And then my drawing function needs to also look at that. So my drawing function used to set everything to black, but now it checks the highlight variable for every single intersection, and it'll draw it in red if it's highlighted and black otherwise. Does that make sense? Everybody with me? Okay, so let's go back to a demo here and build this. Okay, so zoom in so I can see better, and now I started clicking on things, and so I highlight a couple, and I drag stuff around. Whoops. Let me say I ran the wrong program. I think this is the old one, sorry. Let me close these. It's because I've got it actually both of these. Okay, let's get rid of that. That's stupid. Okay, so let's properly update the code. All right, so now I should be able to, I clicked on that, but nothing happened. Okay, I click over here, nothing happened. Click over there, nothing happened. But now if I drag the window, they show up. So click there, nothing happened. But I drag the window and it shows up. There, nothing happens. But I zoom in. Okay, so what's going on? Let me show it one more time. So I'm over here. I just clicked my button. Nothing shows up. But suddenly when I move, I pan the screen, it shows up. What's going on? Why is that happening? So I think it's probably better than what I had before, but it's still not great. So what am I doing wrong? I'm close, okay? So I'm mostly right, but I'm not quite right. What? Yeah. Yeah, so basically I'm changing the state, but I'm not forcing a redraw. So it doesn't show up to the user until he or she forces a redraw by like doing something else. So that's pretty counterintuitive, right? Person gets no immediate feedback. I don't want to force them to do a zoom in or zoom out. That's not going to make my TA happy either. So the fix for this, well, you already told me what the fix is. And let's see. So the fix is that we can, the EasyGL application has another member function called refresh drawing. That forces an immediate redraw. So if you know in a callback function that you've changed the state and you want an immediate redraw, call refresh drawing. This will fix our problem. The other thing I'm showing you here is I know the intersection ID, and I'm doing a little bit of string manipulation here. So I put it in a string stream to kind of format it. And then I'm calling another function the EasyGL application has called update message. So I'm basically going to put this message, intersection, and then the name in the bottom. There's a little bottom message area that the default user interface layout we've given you is. This update message writes things to there. So if you want to write a one-line message, you can do it really easily. So I'm going to show you a demo of that. And let's see, so let's go back here. Okay, so let's run that, and this one should work. Okay, so now I click on things and they'll actually highlight right away. Some of these are underneath others, so they don't show up so well. Let me zoom in a little more so I can make sure there's less overlap. Okay, so I click on these and it all works, and if I move it around, they don't go away. Okay, so I've now got a proper renderer. It immediately gives feedback, but I don't lose it. So that's the right way to do it. One more thing I'm going to show you. Okay, so let's see these two boxes. I'm going to click on, you can see where my mouse is. I'm clicking on a certain intersection, but it's the one that beside it that got highlighted. Okay, so let's maybe take this intersection. I click on it, and the one above it got highlighted. So let's see, let's click on this intersection, and the one to the right got highlighted. So my clicking doesn't seem very accurate. What's going on here? Yeah. Yeah, so I didn't do I drew my intersections kind of where they are, but I actually draw it from the lower left corner and then going up 100 meters and to the right 100 meters. So my intersection is actually at the lower left corner of this. So it's my find closest intersection is finding what intersection are you closest to, but that's the lower left corner. That's a bit confusing to the user. They would think the middle is what I should click on. But we're not checking, are you closest to the middle of this rectangle or that rectangle? We're actually checking, are you closest to the lower left corner of this rectangle or that rectangle? So I kind of haven't done a great job of lining up where do I click with versus where are the intersections? So it's a bit offset, it's a bit annoying. How do I fix that? It's not hard to fix, but what should I do that's better? So what do you think? How would you fix this? So you're right, you diagnose the problem, so what's the solution? Yeah, if I draw the boxes centered on the intersection, then if a person clicks in the center, they will get that intersection, and that is intuitive to them, right? You're gonna basically highlight whatever box you are closest to the center of, and that matches the way people want to think about this. So that's the way I should draw this. And that's actually what I did in the very next version of this. So I'll show you the code in a second, but basically the next version just draws it slightly differently. And it fixes this issue. Okay, so I click there, I get the right one, click there, I get the right one, click there, I get the right one, there. Okay, so basically now it lines up, right? It feels natural. So yeah, so pay attention to kind of fit and finish issues like that. Okay, and the fix for that select not being accurate is pretty easy. Okay, so basically all I did was I said, well, if I have the XY location of the intersection, let's basically draw a rectangle that is centered there. And all I have to do is shift my lower left corner by half the width and height, and the rectangle is now centered. So it's pretty easy. And that's all I did in the last demo. Okay. All right, so that's it for like, how do we handle mouse clicks in the user area? One last thing I was going to show you is how do you add buttons? Okay, so far we haven't added any UI, what are called widgets. Widgets are like things like buttons and dialog boxes. So I want to show you how to add a very simple widget. It's like a clickable button. So it's a button you click on, and when you click on it, a callback is called, so you can do something. So how do I do that? So I'm going to make a pinkify button. So what this button is going to do is when you click on it, it's going to make the background pink. Click on it again, it'll make the background white again. So what do I need to make that happen? First I need to create this button. So EasyGL won't create this button by default. I have to ask for it. It's my new button. I can't create that button until the window exists. Doesn't make sense to create buttons in a graphics layout. Well, graphics window doesn't exist yet. So I have to put this in an initial setup routine. Like I need the window to be created, and then I need EasyGL to call some more code. It's going to add some stuff. So what I do is I register another callback. the initial setup callback. Then I've got to write that callback. And in that callback, I'm going to write a little bit of code to create the button. And the button itself gets its own callback. Like when you click on it, I have to say, here's the callback you should call. It's going to do something useful that I wrote. And what we're going to do is we're just going to have a global variable called pinkify that is either on or off, right? True or false. Every time a person clicks it, we just toggle the variable. And then the last thing I need to do is change my screen redraw function to pay attention to this variable to draw the pink background or not. Okay, so let's look at what that looks like. And this is basically a procedure for any buttons you want to add. So first, I need to specify this initial setup callback, and I'm just going to call it initial setup. And it's the first parameter to application run. I now need to write it. Always has to have the right function signature. So it gets an application pointer, the ece297 application. It also gets a Boolean variable that says whether this is a brand new window or not. I don't care about that. To avoid compiler warnings, I'm going to comment out the name of the variable. That's a standard way to say, even though I know I have a bool that got passed in, I'm telling the compiler I'm not going to use it on purpose. So I just comment out the name of it. I cannot just delete it. If I delete it, I don't match the function signature. I won't compile, and if I did manage to compile, I would crash. So don't do that. And then I don't have much to do. So ece297 has an easy method to create buttons called create button. So I just call it through the application pointer. I tell it the name to put on the button. I tell it what row in that column of buttons it should go into. And I tell it the name of a callback function. Whenever it's clicked, that callback function will be called. And then I have to write that callback function. Okay, it also has to have the right signature. So you look at the documentation, it says the signature is, it gets an ece297 application pointer. I usually need that because I kind of want to do things through ece297 calls. And it also gets passed a pointer to the lower level graphics library GTK widget. I don't need that. I'm not going to do anything with it. I can't delete it, so don't do that because that'll be the wrong function signature. I tell the compiler I'm intentionally not paying any attention to this by commenting out the variable name. Okay, what do? I update my global state, so I just toggle is pinkify on or off, and then I basically say refresh the drawing because I know I've changed the drawing state, I want to redraw. Okay, the very last thing I need to do, well, I need to make my global variable. So I'm going to make my global variable, and I'll default it to off, right? So it's constructed to be false. And I need to make my screen redraw function pay attention to it. Okay, so how do I make my screen redraw function to pay attention? Well, check the global variable. If it's on, I actually want to draw a pink background. ece297 has a routine called get visible world. Okay, the world is basically basically your coordinate systems. The coordinate system you created is called world coordinates, as opposed to pixel or screen coordinates. And I'm asking ece297, give me a rectangle that tells that lower left corner is the bottom left part of my coordinate system is visible, and the upper right corner is the top part of my coordinate system is visible. So it gives me a rectangle that corresponds to the whole graphics area in my own coordinate system. I set my color to red, green, blue. This actually makes pink. I experimented. And then I basically say, fill a rectangle with that color. How big? The whole visible world that it's got. So basically the whole graphics area, the main canvas. I draw this first. Is it important that I draw this first in my screen redraw function? What do you think? So is it important that I draw this first, or it doesn't matter? So you say it's important. Why do I have to draw it first? Yeah, so it's the background, order matters, right? I want the background to be drawn first. Whatever I draw last is on top, okay? So this has to be first. Okay, so if I do that, I can now demo my amazing pinkify feature. And you can even see it didn't take very much code. Okay, so let's comment that one out, and this is my last demo. We'll do a few more after reading week. Okay, so let's run this. Okay, so I click the pinkify button, the background turns pink. Click it again, turns light. If I zoom out, the whole thing stays pink. Zoom in, it stays pink. The Pinkify button works perfectly. Okay, so I have my first extra feature. Okay, so that's it for today. I strongly encourage you to start Milestone 2 over Reading Week. Right after Reading Week, we'll talk about how you can do a quick overview of how you can talk to GTK, the underlying graphics library, if you want to get more user interface widgets. But you now know everything you need to completely finish Milestone 2. You also know everything you need to do all the visualization, right? So GTK is only useful if you want to create additional, more fancy user interface widgets. You know everything you need to know now about how to visualize the map. So I would suggest you go work on all that. Okay, have a great reading week, everybody.
So, yeah, I know it does.